Hello and welcome to Beamer, folks. I thought it was about time we explored the reference of this instrument. I've used the Zener diode. It has its advantages and disadvantages. It's the 4.7 volt Zener. I cannot, if I drop the compliance voltage down to below 5 volts, the 4.7 volts will move downwards, so it's not a very stable reference. As you increase and decrease the voltage here of the compliance voltage from say below 5 volts to maybe 30 volts, you change the current through R1, which affects the Zener diode, and the Zener diode voltage will change very slightly. You can compensate for this, and instruments of old used, some of them used Zener diodes, and the way you can improve this is by selecting Zener diodes. So you'd have a whole box load of Zener diodes, and you would go through them, checking them for per degree C change. So you're looking at the thermal change here, and you're looking at the overall performance of the Zener diode, and you can select a Zener diode. Maybe out of 1,000 Zener diodes you can get a couple of them that perform very well. You can also compensate for the percentage drift per degree C by including a conventional diode in series here with the equal and opposite percentage shift per degree C as a Zener diode, so therefore you maintain stability on your reference voltage that way. You can also include here a constant current source, so that you only have a fixed current going through the Zener diode, and thereby stabilizing its reference. You can also put a Zener diode within a small oven, and the oven will keep a fixed temperature, thereby establishing a fixed voltage here. But all in all, Zener diodes have been superseded by integrated circuit reference chips, some of which can get very expensive. In days of old, when nights were bold, this type of instrument would use something called a Western cell. I've worked with Western cell devices before. They are a chemical product, and this is of course where standard references started from. They used a chemical cell that was stable, but there were one or two disadvantages with it, quite significant. One is that it takes time for them to physically settle, so if you move the instrument, the voltage won't stabilize until maybe an hour later. You can get bubbles within the chemistry which affect the voltage, and per year you get a slow dissipation of voltage, slow drop of voltage, and I think it was 50 or 60 microvolts on drop on a Western cell. So you'd have to send your instrument off to be effectively recalibrated periodically. But all in all, quite a disadvantage. So what I'm going to do here with this instrument doesn't really warrant a really high performance, expensive reference chip. I've got economics in mind, but I do need to replace the Zener diode. I need to get its voltage down to say 2.5 volts, something like that, so that I can drop the compliance voltage down below 5 volts. So I'm looking at replacing this Zener diode, and that's what I'll do next. I'll show you my idea and my chosen device in a second. Okay, so this is circuit D. Let me just say something about the Western cell. Incidentally, I'll put a link down below the video to information regarding the Western cell. There was one other thought that occurred to me, and that is you can never draw in any sizable current. Always had to have a very high impedance load. The chemical cell, the Western cell, was not built to provide current the way we kind of know it as a, let's say, a AA type battery, where the object is to draw current from the cell to drive, say, a LED. A reference cell, Western cell, is not that type of structure. It is not designed to provide current. Okay, moving on to my chosen device. It's the TL431. Again, I'll include a link below to the data sheet regarding this device. It's very economic. You can pick them up for pennies, and they're actually quite good. I didn't particularly worry about the output. It's 2.5 volts. It does vary from device to device and depends on what category of device you order or obtain. That voltage can always be trimmed out in R2 to the exact voltage required. The required voltage, I don't know whether you've noticed here on this circuit D, but I've changed from 100 ohms down to 33 ohms. That means for 0.33 of a volt, you would be placing 10 milliamps as an output current on this sync circuit here. So I've dropped the voltage from effectively 1 volt down to 0.33 of a volt. So therefore my reference voltage only needs, I've got 0.38 of a volt here, allowing for a little bit of tolerance. So I only need to derive, I only need to have on the positive input of the op-amp here a maximum of 0.33 of a volt to achieve 10 milliamps. And you can range select that resistor here to 3.3 ohms or 330 ohms or 3.3k perhaps, or 0.33 of an ohm. Those can be derived by paralleling 10 ohm resistors or 1 ohm resistors, etc., to obtain the 3.3 number. Right, going back to this device, the TL431, it offers about 50 parts per million per degree shift. That translates to across the full temperature range of, let's say, 0 to 70 degrees C. That translates under 1%. So the TL431 has a resistor driving here to drop the voltage, produce a certain fixed current for a certain compliance voltage here. If you vary this compliance voltage, similar to a Zener diode, you vary the current through this resistor here as you increase or decrease the voltage on the compliance voltage. That in turn changes the dissipation, the heat that's produced inside the TL431. That affects the temperature coefficient drift of the device. So I went through a number of 1 or 2 configurations in my design to see whether I can improve upon that. And let me just move through to how I explored the TL431. Okay, this is the first thing I did, which is basically the circuit above. I've got a 5 volt DC compliance voltage here. I've got a resistor setting 2 milliamps going into TL431, and you've got the dropper resistor going to the potentiometer and the wiper of the potentiometer going to the positive terminal of the op-amp. It's the reference voltage. Now if I were to increase that compliance voltage to 30 volts, you would get a significant increase in current going into TL431. That in turn produces heat and affects the parts per million drift of the device. So I found a solution to that helped the situation, and that is here. What I've done is I've produced a very simple current source network here where it supplies effectively a constant current through to the TL431. So now it doesn't matter whether this is 5 volts or whether it's 30 volts, you will still get a constant current feeding the TL431. Therefore, a constant thermal dissipation in this device. Using a 180 ohm resistor here in R18, I obtained a 3.9 milliamp current going into the TL431. This device, basically the constant current source, it's a fairly cheap, inexpensive way of deriving a constant current source. You can do it many ways, but this is probably the most economic way. You can actually do it with an FET, but you're up against the source to gate voltage being quite high. And obviously if I want to drop this voltage down to a low voltage, that's a disadvantage. So I stuck with the transistor, the BC556 PNP dual transistor configuration here. So what's happening here in this constant current circuit of Q15, Q16 is that the VBE of Q15 is establishing 0.7 of a volt across the 180 ohm resistor there, and that provides, and that is translated by Q16 into a constant current feeding the TL431. So if I have pulled out my calculator, if I have 0.7 of a volt divided by 180 ohms, that establishes 3.888 reoccurring, so that's 3.9 milliamps of current flowing into the TL431. The TL431 can go down to about 1 milliamp of current, so nearly 4 milliamps is putting it at a fairly safe position. It can actually you can feed the TL431 up to 100 milliamps, but that would produce quite a bit of heat within that chip. So having 3.9 milliamps feeding into it all the time, irrespective of the compliance voltage, is a very good thing. This circuit I've chosen over an FET equivalent circuit or a single PNP transistor with a Zener diode and a resistor or two resistors. I've preferred this circuit because it goes down to a lower voltage. Your reference voltage is only 0.7 of a volt across that resistor. So again, it favours going slightly below the minimum of plus 5 volts DC. And bearing in mind that the TL431 outputs 2.5 volts DC. So this is the circuit that I kind of preferred. And bearing in mind the source circuit would need, a mirrored version of this circuit. So effectively we need two TL431s. One of the other sort of permutations I played with is this one, which is slightly interesting. I totem poled two TL431s here, one for the source reference and one for the sink reference. And given the price of these chips, actually, you can do this quite willy-nilly, really, because they're quite inexpensive. And in the middle of the two, instead of a resistive dropper, I've gone for, again, a constant current, the one I just showed you, constant current circuit, and it works beautifully. The only problem is with it, the minimum voltage required would be somewhere around 5.5 to 6 volts, which kind of put me off this, although I quite like the look of it, put me off this circuit. It just doesn't quite go down low enough. So what I kind of settled on is a separate TL431 reference for the sink circuit and the source circuit, and this is my favoured final circuit. You've got the constant current circuit here of these two transistors. You've got a minimum. I've got 3.5 volts DC. I don't think I'm going to quite achieve that, but that is the minimum that's required. And then you've got the TL431, and then you've got these resistive droppers. Well, the R15 would be effectively a trimmer, ensuring that the maximum voltage you can get on the output here is 0.33 of a volt. You've got the 10K resistor here, which is the coarse adjustment, and then you've got a 1K variable resistor potentiometer here, giving fine adjustment. Because this circuit is precision, perhaps in a small way precision, but nevertheless precision, it's nice to have this sort of vernier attached to this adjustment. And as far as the reference is concerned, that's about it. All I've got to do now is implement it on my proto board and see how it works. This is Beamer signing out for now.